Hello everyone and welcome to this session. And in this session, let us discuss about illumination model. So in the previous session when I was discussing with you, I discussed about the color model, and using those color models, so we can now talk about illumination model, the surface rendering, how exactly the interaction of the light is going to be used with the surfaces, and whenever these interactions and the illumination should happen, it's going to happen with the color models. Hence in the previous session we have discussed about the color models. So keeping that as an information, now let us discuss about the illumination models. And now when I talk about illumination model, so which is also called as lightning model or the shading model, because if you just observe this particular object, now this is going to be a sphere. If there was nothing called as illumination, this would have been looked like a flat circle. Though I have been drawn a sphere, it would have been look like a flat circle. Hence now we have brought the lightning model into the effect by bringing the camera, by bringing a light source, and by discussing how exactly the ray of the light is going to incident on this and what type of color it's going to reflect back. All this component will tell me what is the color the sphere should look into the viewer and what color the points on the sphere should look away from the user, and that is what we call this as shading model. Now if you just observe, so there's going to be an uneven shading of the surface on the sphere, due to which it is looking realistic to be a sphere. Hence when I'm going to talk about illumination model, which is also called as lightning model and also called as shading model. Hence the color calculation of an illuminated position on the surface of an object is what we call this as the illumination model. Hence now keeping these points in mind, now whatever the process we carry on to bring in the lightning model, to bring in the shading model or the illumination model, we call this as surface rendering methods. Using the surface rendering methods, we can achieve any of this. And what is surface rendering method? It is just the color calculation from a illumination model to determine the pixel color for all projected position in a scene. That is, if I want to project this sphere on the display screen, I should know what is each pixel color value is going to be. That is, all this pixel will be white, all this pixel will be black, and in between this it's going to be of some gray color. Hence, so all this calculation, what color each pixel on the display should be, to make sure it's going to be a 3D object with the proper shading. That is what we call this as surface rendering method. Hence when we are going to have a surface rendering method or the lightning method or shading method, all this always involves two elements. We need to have a close look on these two elements. The first element is accurate representation of the surface properties. That is, now when I talk about a surface, the surface can be shiny, the surface can be rigid, the surface can be the reflective, total reflective, and so I should be accurately represent or tell what type of surface where the light what I am going to define will be injected or incidented on. Hence the second important element is we need to have a good physical descriptions of a lightning effect. Hence I have a surface and I am going to have a light source. The light source will emit the light rays which will be injected on the surface, and know what that the surface does. Hence all this description should happen. I should tell what is the property of the surface is going to have and what the light is going to have its own property. That is where the two important elements we need to bring into picture when I'm going to talk about the illumination model. And so with these two elements to have, so when I say surface rendering and the surfaces, wow, it is going to have a accurate represent to the physical nature or the actual nature. So surface can be reflective, that surface can be transparent, or it can have transparency, or I can put some surface texture to bring in the rigidness in the surface, or even if I'm going to work on the shadows. So a few of the advantage or the outcome when I talk about the surface rendering method. And so now when I'm going to talk about surface rendering method, I told you it's going to be of two steps. The first step is we are going to define the surface property. The second is we're going to define the light property. That is what the light source. We use the light source to define the light property, and the basic illumination model to define the surface property. Hence we are going to have two concepts, two key concepts which we need to look into when we talk about a illumination model. And if I talk about a light source now, it's an object that is emitting radiant energy. In a scene, I may have a light source which is emitting the radiant energy or the light source or light energy, and that object now we call this as a light source because it is emitting some radiant or some energy. And so now we are going to have an object in the scene as a light source, or there may not be any object which is going to be a light source. Hence this light can be of variety of shapes, and it can have different set of characters the way we are going to put into. Hence the light source now can have position where I want to position the light source in the scene as even it's an object, and the characteristics can be of a color, what type of color the light is going to emit, and what the direction of the light source is going to be, and what the shape of the light source is going to be. Now keeping this characteristics of a light source, we can have main categories of the lights, the light source, and in that we have got 5 main categories. Using any of this property by eliminating or by variation, we are going to have this set of different types of light sources. The first step is the point light source, which is going to have a point as a light source and emit the rays uniformly all around the scene in a given definition. And the distant light source, the radial intensity source, the directional light source, and the spot light source. We'll see one by one what exactly this light source is going to be. When I say a point light source, we're going to have a point which is going to be the point of light source where the rays is going to emit, and this point light source will emit the rays all around its point in a circular fashion or in all angles, and whichever the line is going to be in straight with the view of the object, so that ray will be incidented on the object, and the object will acquire the shading property from the point light source. Hence we are going to have a light source. Any one of the light direction will be incidented on the object, and if I can position this wherever I want, and when I position this, the light rays will be chosen with which is going to be in straight in view with the object, and this is what the point light source is going to be. And now if I'm going to talk about a distant light source, we are going to have a point light source. For example, before I can bring in distant light, just look at this. I am going to have a point source, and a ray or a single ray or set of small portion of the ray which is almost intact with the view of the object will be incidented if it is a point light source. And now if it is a distant light source, it is not one single ray which is going to fall on uniformly on this object. It is going to be multiple number of rays which is going to emit itself or energize itself to have effect of its in the complete scene what you're going to deal with. And for the best example of distance light, it's going to be the sun, and the sun will emit the rays all around its surface, and all the rays will make sure will be reaching all the object incidented surfaces. And the sun is the best example what we can talk about the global light source in the scene. And this is the distant light source what I'm going to have. And if I talk about a radial intensity source, so now whenever we are going to have any light energy which is incidented on an object, the object which is closer should be bright enough than the object which is far for the light source. Hence, now we should talk about intensity. We need to talk about the intensity of this light sources. That is what we call the intensity attenuation, which now we need to take into account. Hence, we call this as radial intensity source. And the radial intensity source or the radiant attenuation is computed with the distance of the light source. Hence, we call this as DL. So L stands for light source, D is distance. So depending upon the distance of the light source from an object, I am going to apply this formula. This A0, A1, A2 is going to be the component of a scene or an object, and the D1 or the DL and the DL square is the distance of the particular object with respect to the light source. And this is going to be the radial intensity source, and this radiant intensity source is going to be 1 if the source is at the infinite. If there is no point light source in the scene, we're going to have this as 1. That is, all the object will have, or the entire scene now is going to have an uniform intensity. If the light source is going to be the local light, then the intensity changes. That is, it depends upon the distance now. If a light source is going to be at the infinite distance, then there's going to be uniform intensity as 1. And if there is going to be a light source in the local scene itself, in that case, the intensity will vary depending upon the distance of the light source and the object. This is going to be the radial intensity source. And now if I am going to talk about a directional light source, so now we are going to have a light source, and now we'll work only on the direction of the light source. There is no angle, there is no any incidented ray. We'll just work from where the light source is entering, and we'll work on only those light rays which is going to be intact with the object. This is what we're going to have, the directional light source. And if I talk about a spot light source, it is a variation of a distant light source where I'm going to have a direction of the light, and I'm going to have a light source. I'm going to have direction and light source, and I'm going to work with an angle, so which is going to give me the spotlight source of the light which I am going to define in the scene. And now if there is an object and it should be illuminated by the light source, then I'm going to work with one more angle of how the object is going to incident in the spotlight, which is going to be of a cone axis vector. And so this is how we are going to have the spotlight in the scene. And so the different types of light sources what I am going to have in the scene when I am going to discuss. So just to have a comparison of what all this light source is going to do, just look at this. I am going to have a point light source, that is I am going to have one point source light which emits the rays all around its surface, and all these rays, one or the other, should be incidented on the object in the scene. Hence the point light energy or the light will be emitting and will be incident on the entire scene because of this uniformity. And when we talk about the directional light source, I know what is the direction of the light source, but exactly I don't know where is the point. And now if I am going to know the point of the directional light, and with the angle will give me the spotlight. And so this is just about the intensity. This is just about how far the light is going to be. or the infinite distance where the light is going to be. The major observation what we need to make here is the point light, the directional light, and the spotlight. Clear? So now with this, just look at one more image over here. So now if I talk about a point source, the rays is emitting all around. And if I talk about direction, we're going to have only the direction of the light from where the rays are coming in. And if I talk about a spotlight, I'm going to have a directional light source. Along with the direction, I'm going to have point of emission. And with the angle, if I'm going to set, it is going to be a spotlight. So the different types of light source what I'm going to have, and that's the first step. The second step is I need to define what is the surface property is going to be, as we call this as basic illumination model. And this basic illumination model will act as an interaction between the incident of the radiant energy. Whatever the light source is going to emit the radiant energy, the incidented light ray, it is going to be the interaction between the material composition, the surface matter, the surface property. So this is going to come into picture, the interaction between the surface and the rays of light what will be injected on that. That is what we call the basic illumination model. And due to this, I can just have a surface, so which is going to transmit the ray of light, or it can totally reflect the light, or it can absorb the light, or it can scatter the light. So depending upon this image, I can roughly make out the surface is made up of different types, which can absorb, which can reflect, which can transmit, which can scatter. Hence, now we'll see how exactly we can bring these few properties into the picture. As when I say basic illumination model, so the three basic illumination model which we can bring in as an interaction of the radiant energy with the material or on the surface property. The first one is the ambient, the second is diffuse, and specular. When you talk about the illumination model, these are the three which you need to focus upon. And so when I'm going to say an ambient, right, this is the general brightness level for a scene. So it's going to be uniform brightness level all around the scene if I'm going to use the ambient light. Hence in the ambient light, I don't know from where the light ray is going to come. In whatever the point the light ray is going to come and injected on a surface, is a uniformly is going to radiate or it's going to reflect all the light rays all around its surface. That is what the ambient light is going to be. Hence non-directional light source, because the direction is not fixed here. And usually this is going to make use of the background light whenever it's going to illuminate the scene. And the amount of incident on each object is constant. Whatever the energy or the intensity has been incidented is going to be constant in ambient light source. And the constant for all surfaces and overall direction is I'm going to have a constant or uniform reflective rays when it's injected on a surface. And this is very simple model, but if I use this won't be a realistic image. This is not going to give me a realistic image in my scene. And so when I want to bring in the illumination, the reflectionness of an ambient light, this is the form what I'm going to use. I'm going to compute the intensity of ambient light in my scene, which is equated with the surface ambient reflection, the amount of reflection what the surface can make, multiplied with the intensity of the light. The intensity of light what I'm going to have, this black lines what you are seeing, and the surface property in the form of K what you are seeing, and the white arrows what you're seeing is the intensity of the ambient. Hence now this K belongs to the range of 0, 1. It can be anything between 0 and 1, including 0 and 1. It can be anything in between. Starting from 0 until 1, it can be any value. I can vary this value in this case. Hence, so in principle, So this ambient light or any of illumination model, we talk in terms of colors. Hence this IA should be a color. So this IA is going to be a color, and even the K is also a color component or color function. Hence, so this should be expressed in the form of red, in the form of green, and again in the form of blue. And ambient light should be expressed in all these three forms of color. Whatever we derive it generally, but same should be applied for all the three primary colors. And now with this, we are going to have a diffuse light. So now just look at the difference here. So when I'm talking about the ambient light, I had no direction. I had no direction of a light. The incident of a light ray was all around in the scene uniformly, and the scattering was happening uniformly. Now in diffuse, there's going to be a point, there's going to be a source point, and now I am going to have a direction, and when the incidented, I am going to uniform scattering. Hence, in ambient, I don't know the direction, I don't know the angle. But in diffuse, I know what's the direction and I know what is the angle of incident. Hence, so such surfaces are called ideal diffuse reflectors. Fine. If I'm going to have uniform reflectors, we're going to call this as ideal diffuse reflector. So now this is also known as Lambertine reflectors, because this is going to work with the angle of incident and the angle of reflection what we are going to take into account. Hence we are going to call this as Lambertine reflectors, and Lambert-Cosin law will be used whenever I want to compute what is the scattered ray of light when it's injected on the surface. Hence the brightness at each point is proportional to the cos theta. Now whatever the surface point brightness is going to be, it depends upon each point, which is proportional to the angle and with respect to cos theta. And the surface perpendicular to direction is more illuminated than the surface at an angle. That is, now if I am going to have a perpendicular surface, for the rays what is going to implement will be having more illuminated surface than what we are going to hang for an angle what we are going to form with the surface. Hence this is what you need to understand when you're going to have diffuse light. And if you want to put into equation, so now I diffuse, that is the incident illumination of an diffuse light is going to depend upon KD into IP. So where IP is going to be the point light intensity, and this is multiplied with the cos theta, so which is going to give me the angle of scattering over the surface. Hence we are going to have cos theta, and KD will again vary between 0 and 1. And now this cos theta, now we are going to have a theta over here. Now this theta depends upon the normal vector and the ray of light which is incidenting. Hence we are going to call this as Lambertine image. And so now with this we are going to replace cos theta and need not work with the theta now. I am going to multiply the normal vector with the Lambertine vector or the L vector. Hence we are going to have N as the surface normal and L is going to be the light direction. So instead of having cos theta, I am going to have N into L. And when I am going to have this diffused light, now this diffused light is going to be the form what I discussed if N into L is going to be greater than 0. If N into L is less than or equal to 0, in that case the diffused light is going to be set to 0 or nothing. And so now again this diffuse should be expressed in the form of red, green and blue, because this incident is only general. Now this should be brought into all the three color variations. And now when I talk about an ambient alone, it doesn't give me a realistic image, and diffuse alone will never give me a realistic image. Hence if I want to have the realistic image, I am going to talk about the ambient plus diffuse, that is I equals I diff plus I ambient. And you know what is the form for I ambient and the form for I diffuse, I'm just going to replace this with this equations. Now this is going to give me the equation with the ambient plus diffuse. So now this incident of ray, which is a combination of diffuse and ambient, should be expressed in all the three primary colors, that is RGB. Yes, now this is what happens when I'm going to mix the ambient plus diffuse. So now if I'm going to increase the ambient, I'm just going to have an uniform scattering without any direction. There's no direction. And if I'm going to have the diffuse, as I'll be moving or I'll be increasing the number of parameters with the KD between 0 and 1, I can see there is going to be a shading and there's going to be direction of light also. Now this is the direction of light because this is a surface which is more illuminated than the behind scene or the behind points. And further, if I increase both K and KD, this is what I'm going to end up with. And this is ambient and diffuse. And the third type of illumination is going to be the specular light. And whenever you want to have a bright spot on a shiny reflection or a specular reflection which is going to occur on a shiny surface, we're going to talk about specular light, where I'm going to have a point source, a point ray with an angle. I'm going to have one sharp ray which will be reflected. If it's diffuse or ambient, we're going to have set of rays which is going to scatter. But now I'm going to have only one ray which is going to scatter. Now just look at this image now. You'll get an idea what exactly this specular is. Now in this sphere, you can just see a point, a bright spot which is reflecting strong enough towards the user. And now due to this bright spot, it appears to be shiny surface. And this is the specular reflection of a source. And the point directly facing the source. Hence it is going to be a bright spot. And you can just look at what is diffuse light and uniform scatter and specular reflection of the light from the tabletop. So due to this reflection of the tabletop, I am going to have one more specular here. So you can just observe the image and you can just go through this, what exactly this is going to mean for you. And you'll clearly understand difference between the diffuse lighting and specular lighting. And now this is the surface, so which is going to have a sharp angle of incident and I'm going to have one ray of reflection. But whereas in diffuse, the rays is going to get scattered. Now due to this property, the surface will be the reflective surface or a shiny surface, and this is going to be the rough surface if I talk about a diffuse lighting. Hence now when I'm going to have a specular light, so which is going to models, if I bring in specular, this is going to make the model or object to be shiny and glossy surface, and which is going to have one sharp point which we call this as highlights. And now this is idle. This idle, or when you're going to have specular light, the idle specular surface reflects light exclusively in one direction. This is what I'm going to have idle specular surface. I'm going to have the light of incident and light of reflection is going to be same, and it's going to be only one ray or one exclusive direction what the reflection is going to happen. This is going to be idle specular surface which creates sharp point or a bright spot on the surface. Whereas when I say non-idle, so I'm going to have reflective ray can be in any of this range. It can be in any of this range, and now this we call this as non-idle specular surfaces. And now when we bring in the specular light, and if I want to see the real effect of specular light, we are going to make use of the Phong model. So Phong model, including the Phong model, will tell me what is the specular light is going to be. Hence when I talk about specular light, we need to talk with in combination with the Phong model, or when I say Phong model, it's again a specular light. Hence if I want to put into the form, so I specular is going to be depends upon Ks multiplied with IP, the same IP, the point light source which I had brought in discussion in the diffuse, and the cos n phi. Hence I'm going to have the pi value. What is the specular angle of reflection is going to be, and n is going to be the reflection parameter derivation from the ideal specular. Now from this I am going to derive what is the n is going to be. This is going to be the ideal reflecting ray, and whenever we are going to ideal specular, the value of n is going to be at infinite. If you want to have one sharp dark spot, the n value should be at infinite. Anything when it decreases, the spot tends to increase, and this is going to depend upon cos and the pi. And now you know what is IP, you know what is Ks. And now with this, I'm just going to I speculation. Now I specular can be replaced with the cos n pi as r vector into v vector to the power of n, where n is going to tell me what is the ideal super reflector parameter I'm going to use. And so now with this having, just look at this diagram where I'm going to set n equals 1. Hence you can see the spot is going to be large. It's going to have large area. And when I'm going to increase the value of n as 8, I'm going to have a narrow spot. And when I'm going to increase further, I'm going to have further narrowed path. Hence if I keep on moving towards the infinity value by increasing the value of n, you're going to get the sharp value or the sharp bright spot on the surface. And now just look at this example. This is the bright spot because of n equals 64, and even if we increase the value of n, this will get as narrow as possible, and n is 8, and so you can see the bright spot is enlarged, and n1 it's still enlarged. So this is how we are going to make use of the specular light. And when I'm going to have a specular light, now this specular is going to be 0 when v into r is less than 0 or n into L is less than 0. So similarly we are going to apply this form when this condition is going to be true. And so when we are going to have a true realistic scene or an illumination mechanism on the object, we should talk about the combination of all these three, the ambient plus diffuse plus specular. I should be able to bring all these three into the picture. And so I'm going to say now the total intensity is going to be equivalent to intensity of ambient plus intensity of diffuse plus the intensity of specular. I'm just replacing the forms of all these three. I'm just replacing all these three forms, and by just taking down the common, because this two will use the point light source, hence I'm going to call this as IP. But where this doesn't use as a point light source, and still we are calling this as IA itself. Hence I'm taking common over here and apply and bring this into the common terms. Hence I'm going to have this as a form when I want to bring in the ambient plus diffuse plus the specular into the picture of the scene. Hence now this is in general. Now I should represent, or I need to present this intensity with the red intensity, the green intensity and the blue intensity with the same forms what I'm going to use. And if there are n number of light sources in the scene, now ambient doesn't have a light source, there's no point source in this, hence there's no need of talking about a multiple light source. But when there's a multiple light source of k number, I need to put the diffusion and the specular into the summation of k light sources. And this is how we are going to make use of the ambient diffuse specular. And just look at this diagram. I'm going to have an object. If there's only ambient, I'm going to have this as an output. The light incidented on this uniformly scattering all over the surface. And if I bring in the ambient plus diffuse, now I know what is the light source. Depending upon the light source, I am going to apply the illumination effect on the object. And now if I bring in the ambient and the diffuse along with the specular, now you can see some bright spots on the scene, so which will now make the object to be the shiny one. Now this is what you should understand about ambient, diffuse and specular and the illumination model. And in the next session, we will be discussing about the OpenGL functions which we are going to use to bring in the light properties and to bring in the surface properties, and how exactly we are going to talk about the ambient, the specular or the diffuse in terms of implementation or the functions what you are going to use. So now, thank you for this session.